So I was looking for the extra credit question from last lecture and I couldn't find one.
Couldn't either.
I did not give. I think I'm
Okay.
resisting doing extra credit now because maintenance is getting a problem because everyone is submitting by email and it is randomized. It doesn't come at the same time. So I have to go in and pick which email corresponds to which extra credit from 4 different classes. And I'm not liking it very much.
Yeah.
I'll give less extra credit so that it's less work for me. Does that make sense?
Yeah.
So I know it probably you guys, if you guys like an extra credit, that might be a loss, but I think that's okay.
I like the thought experiment of extra credit.
So how about this? Maybe we can agree on this if you guys all think it's okay. We stop submission of extra credits. I can keep telling you, think about it. I mean, it's up to you guys, but I won't ask for or I won't grade it. You see what I'm saying?
Yeah, I like the thought experiment.
Keep having it, but
Yeah, that's fine.
If you really want to grade them, you can just ask them to submit one report at the end of the semester, towards the end of the semester, and then you can, if you want to evaluate it, something like that, right?
oh yeah, why not?
You can just ask them to do it every week whenever you give them, and then at the end of the semester, you can just ask them to turn in one report with all the questions and answers.
And all that, and I don't keep track of the dates myself.
Yeah.
Yeah, why not? Like, you guys do that, and we will see at the end how it goes. Like because of all this change of setup and all that, I'm trying to be lenient in this whole thing. I don't want to demand too much, especially the undergraduate classes. It's tricky. I think here, I think I have a good handle. I think, but there I am not very comfortable about the whole thing.
Yeah, it's interesting semester so far.
Yeah, Jordan, you start the semester and everything goes haywire.
Huh?
Poor Jordan.
Yeah, poor me. I wish I could get that sympathy from my wife.
Okay. So we have a homework due. Lots of homework due, I guess. There was homework 7 due today. How is homework going, by the way? So this is homework 8. It's not available yet, but it will be up online. I think it will be pretty much. I'm just going to cut and paste from last year and put it. Sometimes I get this urge to write one question or something, so I might do that. But most probably it's the same as last year. And we have midterm 2 on April 13, Tuesday. So we agreed on midterm 3 being midterm 2, right? Midterm 2 being what do you call take home. And if I provide it before the class begins and like let's say 24 hours or so, and I make it due within that week, I won't even make it due on the day. So you guys can take as much time as you want.
April 13 is Monday.
6 plus 7. That's Correct, 39. Why is that Monday? Yeah, because I wrote it wrong here. So thank you. So that's 14, let's say. So what I was suggesting is that the midterm 2 for this class alone, I post it sometime early in the week. You guys submit it sometime during the week. But in return, you allow me to teach on that day. Is that so? I gain a class.
Yeah.
Yeah, that's fine. We've already
fine.
lost a couple of classes and it's fine totally.
We lost a good number of classes, so I think it will help you finish things.
Yeah.
But I should say that at least for Angela, midterm, the E&M, that won't be the case. But I'm thinking of making it in-class exam, by the way.
E&M?
Yeah. Okay, so that's.
How do we do that?
We have to think about that. We'll talk about that later at 12:30. Something with a camera, maybe, since it's only 2 or 3 of us. So we'll try that. Something like that.
So that's also it's going to be the week of April
I
30.
think that is on, no, that is next week, April 9th, right?
Okay.
Okay. So again, midterm 2, this is pretty much take home. The idea is that I think I think you guys are doing good. I think assessment is not a big deal here. Okay, so. So we want to change gears. We have been actually talking, doing a lot of problems on Lagrangian and the properties of Lagrangian. Now we want to take one problem in particular and work a lot on it, spend a couple of weeks on it. And that is the Kepler problem. It is a very popular problem. It is obviously the most famous problem in the first 200 years after Newton gave his laws. Even today, it is extremely popular. We can understand why it is, because our planets use that same equation. Right? It's the same as same equations that govern a hydrogen atom also. An electron going inside around a proton also is governed by the same equations, except that there at some level we switch over to quantum mechanical interpretation of the whole problem, and that's important in that case. But at least to a certain extent, that's it's very equations wise or analytically, it's exactly the same. Okay. Now, so let's call it the Kepler problem. Most of what I write here under this problem, almost line to line goes in a, if you're studying hydrogen atom, and you will call this a hydrogen atom problem. Okay. Pretty much identically go through, except that every quantity you write is an operator, and here it's they commute. Okay, so what's the point? We have 2 masses. So let's say that is M1 and there is M2. Okay. And we don't, and the only interaction between them is that there is a force between the 2. Let's force. And that force is given by the Newton's gravitational F is equal to G M1 M2 over r square, right? Let's not really say r square because that will involve, if I say r, it is with respect to some coordinate system, the position vector, and that would require for me to keep that one of the masses at the origin. So that's not convenient because then I'm saying that one of the masses does not have motion associated with it. So let me keep that very general. So we will say this is R1 minus R2. Left-hand side is a vector, right-hand side should be a vector, so there has to be a direction associated with this. So let's call that R hat, where R hat is R1 minus R2 divided by R1 minus R2. And I will also specify in which direction this is. It depends on whether you're acting on 2 or 1. Let me say it is on 1, then it is outward, right, somewhere in the outward direction. So R hat is that, has that sign convention which we could point out which force I'm talking about. And by action and reaction by Newton's third law, it is clear that this force F12 will be exactly equal to F21. So let's say this is F12. Is Newton's third law always obeyed in nature?
That's what we've been told.
That's what we've been
Action
told.
reaction forces are there. Forces always occur in pairs, right? That's what I've been told.
Always occurs in pairs. Yes.
But at least that's the question I gave to my undergrad class.
Yeah. That's right. Any other comments?
I don't know if you.
Maybe non-relativistic case, I don't know. I don't know if anything happens in there.
Relativistic or non-relativistic?
Relativistic, sorry, yeah. Don't know if something happens there, but
Here is a thought problem like you guys want, like extra credit, right? So here's an extra credit problem. Okay. So we have to go slightly outside classical mechanics. So let's go to. So let's think of a positive charge, right? Q, moving with a velocity v. Let's call it Q1, and that's velocity v1. If this is a positive charge and if it is moving, that will create a magnetic field. Is that familiar? Right? Any moving charge will create a magnetic field. And if it was a line charge, if it was a current, then it is very clear what its magnetic field is. If it's a point charge moving, it still creates a magnetic field. Its direction is clear. The expression is a little more complicated than what we study in elementary courses. Okay? But still, its direction of the magnetic field will be given by the right-hand rule. So it will come out of the board on up here and go into the board down here. Clear? That's your magnetic field. That's clear what I mean? That's a magnetic field created by one. Is it? It comes out of the board on one side and goes into the board in the board. So let's have another charge now. And that's somewhere here. That's also a positive charge, Q2. And that's moving in this direction. So that's V2. So everywhere on the line below this line along which charge Q1 is moving, magnetic field is coming out of the board. Everywhere on top of that line, magnetic field is coming out of the board. So charge Q2 that is moving will experience a force, right? From charge Q1. What is the direction of the force on Q2? What is the force on Q2 by Q1?
Repulsive force, right? Or
Yeah, that is a repulsive force. First, let's talk
Towards the
about
right.
that is surely a repulsive force, right? So that's let's call that F electric field, and that's F21. Agree? But there is also, that is from the electric field of this positive charge. But there is also a magnetic field created by this charge that's coming out of the board at this point. So what will be the direction of the force, magnetic force on the charge?
Towards the right.
Right, so towards the right, right? So that's your force, FP on Q1. There is an electrostatic force here. It will be the same F of E to 1Q now. And because this charge is moving along the axis to the top, its magnetic field will be coming out of the board on this side, going into the board on the right side. What is the magnetic force on 1 due to 2?
Towards south.
Towards
Down.
Towards down, correct? That's correct. Right, so that's your F of B1Q. And now tell me, so the total force here is somewhere in this direction, right? That's your total force. And the total force here is in this direction. Are they in opposite directions?
Not necessarily.
Well, what happened to Newton's third law?
It fails.
Can it fail?
It fails
No.
in magnetic forces, right?
Well, that's Newton's law. You cannot easily say it failed, right?
I don't think it fails as like when you include this the total system, right? But it fails in like
What do you mean
the
by
what is it
total system?
non-reciprocal, or what was it called, like non-equilibrium. I don't know. I forget.
Yeah, we shouldn't. Yeah, so think about it. Does it really fail? Shouldn't. Newton's third law is. Yeah, does it fail? If it fails, it's
But
big. Right? It's not.
but you can violate it in out of balance systems, right?
What do you mean by out of balance system? In a closed system, maybe that's what you mean by out of balance, means it's not a closed system, correct?
Yeah, I think so.
So by closed system, I mean there is no external force acting on the system. Like all the
Yes.
forces are internal. And it could be moving in the sense that it's going with a constant velocity. That's okay. But as far as it's a closed system, Newton's third law tells us that all
Like when an environment moves with respect to those two particles, right? It violates it.
if it interacts with the environment, yes. But then you can absorb the environment into your system and say that's your total system, and then it will be okay. So
Okay.
every action has to have a reaction, and they have to be equal and opposite. That's our understanding. That's what he told us, and if that is not valid, what will go wrong if the action reaction doesn't work out well? Like, where do you use the action reaction? Where do you use third law? Yeah, maybe that's what I can ask. Where does it play a big role?
When I'm doing push-ups.
Isn't it when two objects don't interact with each other?
Or maybe I can rephrase my question. What is a consequence of Newton's third law? Where does it play a big role? Any conservation principle that's involved, associated with it? How do you derive conservation of momentum? Right, a car comes and collides with another car. During the collision, the momentum is conserved, but doesn't one car exert a force on the other and the other one exerts a force on the other one? So why should the momentum be conserved? Then there are forces involved. You see what I'm saying?
Yeah.
So, for example, if what I'm saying is that if you have one car M1 coming and colliding with another car M2, right? And conservation principle requires that dp by dt, that's your mass times acceleration, is equal to f1 plus f2 or so on, right? That's the sum of forces, that's Newton's law, sum of all the forces has to be equal to the rate of change of momentum. And conservation of momentum is the statement that if all the forces are zero, then momentum is conserved. Then this is equal to zero, then momentum is conserved, right? But the forces are not zero, right? M1 exerts a force on M2, M2 exerts a force on M1, and there's a lot of things going on during a collision. So why should momentum be conserved? But we always say that momentum is conserved.
The two forces are equal and opposite.
Yes.
So the total force becomes zero.
Forces exerted by one on the other, but they all add up to zero. Right? If they all add up to zero, then momentum is conserved. So in this case, if you were to have a system enclosing both the charges, then the forces should balance and then momentum will be conserved. Otherwise, momentum will not be conserved. Right? So what you're saying is that there are two forces not acting in the same direction. That means the whole system should go to the right. Like they should start accelerating to the right. That doesn't happen, right? So obviously something is, what is missing? That's the point. Right?
Well, what's missing is the final conditions, right? Like we've just set up the initial conditions of the system. And
you're thinking, no, that's
okay.
a good point. Good point. But turns out that's not.
Okay.
It's deeper than that, or it's more complicated than that. Yeah, but that's a good point. Yeah. So this is the one instant.
What about angular momentum?
Yeah, that will also not be conserved because these forces are not balanced. Angular momentum also will not be conserved. But linear momentum in as such should be conserved, correct? If there is no external force, it better be conserved. Otherwise, this whole system will start accelerating. So that's for you guys to think. I want to answer that. And actually, it's not easy to answer. Like it's not one of those problems that I can give an answer and satisfactory answer. It's a little out of the scope of this course. Okay, but still, you should know what it is. But I'll answer it next week. Let's say at least I'll give you the hint for what it is. But is that problem reasonable? So we always take Newton's third law for granted. but we should be careful in systems and concluding something from. Okay. So, but we are doing gravity here, gravitational force. And by the way, any other comments on that? Shall I proceed? Go back to the original problem I was bringing. Okay, so we want to talk about gravity, and in a gravitational, when the gravitational forces are involved, at least when there are two masses, then the forces are indeed in the are equal and opposite, and that's the force. And force, this is also a what is it called? Conservative force. That means to say that you can write this as a gradient with respect to a potential energy, and the potential energy of gravity is G m1 m2 over r1 r2. Is there anything missing in this?
Negative sign.
Of gravity? No? There is something missing. How about that? Is the gravitational force attractive or repulsive between two masses?
Active.
Attractive.
Attractive?
I
Yeah.
think there should be negative in the first equation
There could be a negative sign here, correct?
and the first equation as well.
Oh, first equation, I did not specify what R is, right? So in that sense, because I also need to have origin and other things. So I think it is okay probably. Oh, actually here now it is R1 minus R2, right? So that R hat is in this direction. No, yeah, R hat is in this direction, but the force is in that direction. So this is, yeah, you're probably correct. So this is negative, correct? Because here now, right? Yeah, there's negative sign there. That's good. And if I were to tell it as negative of this, there should be a negative sign here. Here it is much more crucial. Here I can escape by saying, oh, I didn't define it very well. But once I write this, that's clear. Then it is, I think, yeah, when I was writing it, I had not written this as 1, 2 or 2, 1. That's why I was right. Okay, clear. So a negative sign means that it's attractive. How do you see this is if you were to plot this energy with respect to, let's say, R1 minus R2, the magnitude of R, it looks like this. And whenever you have a potential energy, think of really as as rolling a ball here. It will all, energy always tries to minimize. Nature has one simple principle that energy is minimized, so it will try to come here. So that means as you roll, it is effectively an attraction, and that's what we see in nature. Okay, so that's your two masses, right? If you have two masses under gravity, what from the basic popular knowledge that we have, Kepler's law, like this is a Kepler problem. We have studied Kepler's laws. Apparently, they go along an ellipse, correct?
Yes.
How should I frame this question? So once you think of an ellipse, formed by the orbit of Earth around Sun. First, I should say that we are ignoring all the planets, like Jupiter. All the planets do not exist. We just have Earth and the Sun. Okay? And the orbit of Earth around the Sun is an ellipse, and that forms a plane. Correct? An ellipse is in a plane containing the Earth, and the orbit as a plane form and the moment you have a surface, there is a direction perpendicular to the surface, and that points in a certain direction. Is that clear what I mean? So once you have an ellipse, you have a plane defined, and that plane has a direction perpendicular to the plane, and that's a unique direction. What's the significance of that direction?
Can you repeat the question?
So if we think of only Earth and the Sun, all of the planets are removed out. So Earth goes around the Sun in an orbit, or there is an orbit of Earth, and that's ellipse. That's an elliptic orbit, according to Kepler. And an ellipse is on a plane, like a plane contains that ellipse. Right? And once you think of a plane, there is a direction perpendicular to that. What is the physical quantity along that direction?
Okay, so I don't really understand the question.
Okay. Let me restate it.
So would this plane contain the, would it like have a section of Sun and Earth as well, like the equator part? Is that how we would imagine it?
Yeah, so let's see. So if you have, let's say this is M1, M2, let's say, and this is your other, right? This is a plane, like this is on the plane of the board. Right? Is it possible that, or my question is, what is a physical quantity that is coming out of the board for the system? What are the physical quantities you can think of for the system? Oh, make it more better. Okay. What are the conserved quantities for the system? Better.
Is it angular momentum?
Yes,
Yes.
angular momentum.
Yeah.
Angular momentum, like if this is going, think of it as a circle, then angular momentum is coming out, right? And does that remain the same? Angular momentum, is it conserved?
I think so.
For the Kepler problem?
I think so.
I think so.
Right? So angular momentum is conserved, that's correct. So we have one is angular momentum. Anything else that is conserved?
Something about the area that is swept, right? Like the sector area.
Yeah, that's what Kepler's second law is exactly that. And that is a consequence of angular momentum. We'll show that that is exactly the same as conservation of angular momentum. And that is pretty much there. Yeah, we see that in other places also. That's almost immediately one can see that. And we'll talk about that later when we're doing the analytic equation. So angular momentum is conserved for the system. Anything else that is conserved? What about energy? Is it conserved?
Yes.
Yeah, total energy is conserved.
Conserved, but also, yeah. And that's nice enough. But now let us say the moment you have an ellipse, if this was a circle, we don't have to worry about anything because circle doesn't have any orientation, correct? In a plane, if I were to draw a circle, it doesn't have any orientation with respect to the center of the circle, correct? But the ellipse has an orientation. This is a, what do you call this? A major axis, and this is the minor axis. So major axis can be chosen to point at some star. You can always say, what's the, what is that star along which the major axis is pointing? Okay. And then the question comes, does this ellipse change its orientation? Okay, is the question clear? Does the ellipse does the ellipse formed by the orbit of Earth change its orientation as it is moving? And if it does not, then there must be a conservation principle, right? First, the question is, does it change or not? If it does not change, there might be a new conserved quantity there, because angular momentum is in this direction.
And this is
Yeah.
the lady's stuff, right? Angular momentum. Well, I forget her name. The lady with the conservation rules.
Oh, another theorem.
Neither theorem, yes. Yeah, I mean, that is the theme I'm using, that if there is a conserved principle, then there must be a physical quantity, some symmetry must be there. But my point is that if this vector, right, is indeed static, doesn't change, that means that vector is, or at least the direction, magnitude, the direction divided by the magnitude, that remains the same. And that's a conserved quantity. And that's probably not related to angular momentum, because angular momentum is coming out of the body. Right? That's a new conserved quantity. But we never talk about it. Usually we talk about angular momentum and energy. And remember, hydrogen atom is very similar, same equations goes through. We have a quantum number associated with energy, quantum number associated with angular momentum, but we never talk about any quantum number associated with the direction and space. Right?
Is that just translational? Is that
No,
not?
it's not momentum conservation like this, because we are saying this has some angular nature to this, right? So it is not related to the conservation of momentum. Okay, so so anyway, so the point is there is a new quantity. It's any name, and it is not momentum. It is not linear momentum. It's a new quantity. It's called Runge-Lenz vector. And hydrogen atom is very special, or Kepler problem is very special. Only this problem has that, and we will see why that is there. And it's all often called an accidental conservation. Because of that, there is an added symmetry in the problem. So the idea again is that once you draw an ellipse, you have a plane describing the ellipse. That remains the same, but the ellipse also has an orientation. That orientation also remains fixed. And that's because of Runge-Lenz vector, and we will derive that either in a homework or here.
That's the The Laplace Runge-Lens? I think I heard of that.
Very good. Laplace Runge-Lens spectrum. So yeah, that's I should be more careful. I want to give credit to Laplace also. Laplace was the first one to do that. But I think often what happens is that Laplace has so much to himself, like he has done so much stuff that people think that okay, let's share it with others.
What?
No, that's not fair. That's not fair. I completely agree. I don't do that, but yeah, I should have written his name. Yeah.
That's like saying if I were to go to work and I painted all the houses before the new guy got hired. Then they hire the new guy and they're like, yeah, the new guy painted this.
Yeah,
You're like, wait, what?
No, I don't mean anything there. It's like Newton, right? I mean, almost everything he did was, and if a small thing has been done by someone else, you say, okay, remove the name from Newton. No, not fair, not fair. so no. So that's the third one. Yeah. And don't ask me why all three names were there. And I think I read about this, and Laplace did it way ahead. So it was many decades later, I think, if I remember correct. Okay. What else did I want to say? Yes. So this is a two-body problem we are going to be talking about. But a solar system has a lot of planets, correct? And remember, right after Newton, there was a lot of activity. I mean, you could predict a lot of stuff, and you really wanted to calculate all the effects from all the planets, right? So you would like to do the third, what is the effect if you were to introduce more masses in there? What is the most dominant planet in the solar system?
Jupiter.
Jupiter, right? And what is the mass of Jupiter relative to Sun? Do you guys know the masses of Sun or Jupiter or Earth?
I don't know why I have the mass memorized for Jupiter, but I do for some reason. It's like 1.9 times 10 to the 27.
That's correct. So, and Sun will be 1,000 times heavier. That's the way to remember it.
That's only like 1,000 times the Earth.
Yes, 1,000 times heavier than Earth and 1,000 times weaker than Sun. Okay, so if you go by orders of magnitude, Earth is 10 raised to 24. You can say 5 point something, but I'm not interested in that. Right. Earth, Jupiter is 10 raised to 27 kg, and Sun is 10 raised to 30.
Can you raise the camera?
Oh, sorry.
No, you're okay. I don't even have the mass of Earth memorized, but I know the mass of Jupiter for some reason.
I know the mass of Earth memorized.
No, the point is once you know one of them, then you just have to remove 1,000 this way or that way. Okay. And again, this is to zero significant digits, like no digits there at all, right? There's only order of magnitude. Earth will be about 5.9 and Jupiter is 1.9.
Well, we're gonna lose a little bit of mass on Earth due to this virus.
Hey, Matt.
Dark, bro, dark, super dark.
Hey, no, the mass is not going anywhere. People are gonna be dead. You're just gonna bury the dead. The mass is still there.
It's gonna disappear.
They don't disappear.
Earth is not shrinking though, I mean.
Going away.
Good point. Okay. Yeah, hopefully we don't lose too much. Yeah. But okay, my point. My point is exactly along that lines. Okay. Now let us say that when we are calculating the motion of Earth around the Sun, we are neglecting Jupiter, correct?
Yes.
How much error do we make?
A lot.
A lot.
Maybe 3 to 5%.
So 5%. Any other guesses? Or guesses or any other Thoughts? Use these numbers.
Hmm.
Jupiter is significantly smaller than the sun. One in 1,000. One
Yeah.
in 1,000 means it's less than a person, 0.1%. Okay.
Mhm.
So the effects of Jupiter on Earth is 0.1% relative to sun. Okay. It is not 5%. So as far as motion of Earth is concerned, you can neglect all the planets and you're good. If you're fine with working in one person. That tells you something about astronomy. Astronomy is a pretty precise field all the way 2,000 years back, because they could measure things to pretty good accuracy. So they could, all this calculation had to be done. You had to include Jupiter to see the effects. But Jupiter is less than 0.1% simply because of its low mass. It's 1,000 times weaker. It has to be 1 in 1,000. 1 in 1,000 means 0.1%. Okay, since mass plays the biggest role as far as gravity goes. So you don't lose much. And what about Mercury? So someone might tell you, oh, we forget about Mercury. We forget about others are negligible. I mean, it will be, even if you introduce it, nothing is going to happen. So as far as you put in Jupiter, most probably you got pretty much most of what you have. But you might have heard of effects related to an unknown planet and so on. Have you heard these stories? Do you know how Pluto was discovered?
No.
It was predicted, by the way. What was noticed is that the outer planets' motion was not accounted for by all these small perturbations. I already told you that Jupiter causes 0.1%, and you introduce each one of these planets in, and you see the perturbation, and it will be all in the 5th decimal. And they couldn't account for the 5th decimal even after accounting for all the other planets. So they said that, oh, there must be another planet sitting there. So they pretty much predicted that there exists a planet there. Okay. And so that was, whenever you predict something before you have seen it, that's much more dramatic. And the same thing happened later, and that is that Mercury orbits were not, even today, do not obey Kepler's laws. Is that familiar?
Yes.
And how do you explain that today? Or maybe let me tell a few more things, and then we'll start the calculation. I told you that this orientation of ellipse stays the same, or should stay the same in a Kepler problem. But it turns out for Mercury, it does not stay the same. That's called the perihelion precision, or the precision of the perihelion of the Mercury. And you cannot explain that based on any of the principles that we know based on Kepler's law or Newton's laws. Okay. And whenever you have such a situation, you say that, oh, since it doesn't explain, you introduce a new planet. But where will you introduce the new planet? You cannot put it outside because it is not, it won't affect the planet so much. So there is a sun here. So the prediction was that there is a planet going around the sun, very close to the sun, but we don't see it because it is so bright. Okay? And that could account for the perihelion position of Mercury, but it was not the case. It turned out that it required Einstein's general relativity to explain that. Okay? So these are some of the general things involved in Kepler problem. And now let's try to explain all these things. We would like to see that these quantities are conserved. And first of all, we should know that this is an ellipse, right? Who told us that this is an ellipse except for the fact that Kepler's law tells us. So we should be able to derive that this is indeed an ellipse. And we will also derive the precision of the perihelion for Mercury or for a planet in general, like any Kepler orbit. Okay, so that's going to be the overall goal. Okay, any questions as such? Comments? So let's begin with the Lagrangian, right? So we have two masses. What will be the Lagrangian for this problem? Kinetic energy. So that's m1 v1 square, right? Plus m2 v2 square. Two kinetic energies, and this is all three-vector. Okay, so let me call it. This is v1 magnitude, v2 magnitude square, and minus the potential energy, right? But the potential energy is already negative, so this becomes positive. G m1 m2 over r1 minus r2. That's it. So that's the total Lagrangian, correct? There is no other interaction. That's the simplest one can get. And we would like to find the equations of motion based on this. What are the quantities this depends on? We have vector r1, we have vector r2, and the associated velocities, right? So this is velocity v1 and that's velocity v2. There is no time dependence because there is no potential energy does not depend on time. So Lagrangian does not depend on time explicitly. Right. So there should be an equation of motion with respect to r1. There should be an equation of motion with respect to r2, and so on. Okay. So in principle, that's how one would go, but it's easier if you were to change coordinates right at this moment itself, because m1 and m2 in principle, how they are going is, so that is m1, this is sun, right? And that is m2, right? That's your m2. Earth is really small, right? And somewhere in between, there is a center of mass for the system, correct? And the center of, where is the center of mass, roughly speaking?
Inside of M1?
Close to the sun.
Close to the sun. How far from the surface of the sun is the center of mass?
I think it is
Probably
inside of the
inside the
surface.
That's inside the sun, right? Because mass, Earth is so tiny that its center of mass doesn't get disturbed very much. So if I were to represent this as a point mass, m1, right, where sun is big, center of mass is somewhere very slightly disturbed. Even that is an exaggeration in a sense. What about Earth and Moon? Is the center of mass of Earth and Moon outside Earth or inside Earth? Or is
Inside Earth.
it's inside Earth? That's a good observation to make. And so it is inside the Earth, even though Moon is significantly heavier, relatively heavier compared to Sun and Earth. Like Earth is 10 raised to a million times smaller. Moon is not a million times smaller. Only about 100 times small. But still,
Is it pretty close to the surface then?
for Earth and Moon, no, it is still inside. It's very, very much inside. Because it's 100 times, since it's an order of magnitude, it doesn't play a significant role. It is still very, Earth dominates significantly. Okay. So it's not nowhere close to the surface of Earth. It's very close to the center of Earth, but not like sun that it's probably few. How about this? Extra credit, right? You guys should, now that you're sending it all the way at the end of the semester. So find out where the center of mass of Earth is. How many kilometers from the center is it? What's the radius of Earth?
6,400 kilometers.
6,400 kilometers. Yeah, a million, 6 into 10 raised, yeah, 6 million meters. 6,400 kilometers. So then the question is, relatively speaking, how much is that? Okay, so if there are 2 points, right? So there are 2 masses. How does the motion happen? So when we say that M2 is going along and having an elliptic orbit, is it going about the sun's about M1, or is it going about center of mass? So let's make it dramatic. Let's say M1 and M2 are not significantly different, so that's your center of mass. Okay. So let's have a system where M1 and M2 are relatively of the same size. You might have heard of binary stars, right? Binary stars go around each other. Both have motion equivalently. So, so that means to say that this will go along. If you go to the circle, it is easier to see. So that's your. So both of them go about the center of mass in along an elliptic orbit, and they also try to stay about the same point. When this is here, this has to be here. So on. And they have to be elliptic. So it's about a center of mass. So that tells us, so that's a hint that maybe R1 and R2 are too much information here, because that's 6 coordinates. So let's reduce the coordinates by making it center of mass. So we will see what do you gain by using a center of mass coordinate. So let's define. So let's define capital R as, what is the definition of center of mass? M1 R1 and M2 R2 divided by M1 plus M2. So let's define capital R to be 1 coordinate, and since we started with 2 coordinates, let's have another coordinate, and that's a convenient one, is because that is what is this? Potential energy depends on R1 minus R2. So let's define this to be R1 minus R2. And we want to redefine or rewrite our Lagrangian in terms of this new coordinates. Okay. So once we have, we can solve for R1 and R2, right? So help me here. So let me move this on this side. So it's M1 plus M2, right? So that I don't have to write it here. If I were to multiply M1 on both sides and or M2 on both sides and add, I get a relation because M2 cancels out. And what happens? So I have M1 plus M2 times vector R plus M2 times vector small r is equal to M1 plus M2 times R1. And did I go off the board? No. And that leads to, did I move it? No. That leads to the relation that R1, vector R1 is equal to capital vector R plus M2 over M1 plus M2 and smaller. Right, so if wherever I see vector R1, I can replace it with a small vector. Do the same thing for R2. So this time I want to subtract, correct? So R2 would be equal to so M1 so this is capital R minus M1 divided by M1 plus M2 times R2. Sorry, capital smaller. I have the relation kinetic energy of the two quantities. So I have to calculate the velocity. So I have to take the derivative of this quantity. So let's calculate that. Or doesn't it move? So let's calculate V1. Pretty much derivative of R1. So that's a capital V. And by capital V, I mean so V here is dr by dt. Let me write it as dr by dt so that there's no confusion. So this is dr by dt plus small velocity. By V, small v, I mean the vector r without any subscript 1 or 2. Same thing, V2, it's dr by dt minus M1 okay. Any questions on that? Let me make sure that, yeah, that's perfect. What we are interested in is M1 V1 square. So we are interested in the kinetic energy, right? So M1 V1 square plus M2 V2 square, and that will be equal to, we have to square these quantities. So V1 square will have a dr by dt. So this is M1 plus M2. That's the first term. When I square this, multiply by M1 and M2. So that's the first two terms. When I do the same thing for the next terms, I get plus M1 m2 square over m1 plus m2 square plus m2 times m1 square over m1 plus the square, and the whole thing multiplied by v square. And then there is a term which involves the cross product or cross of these two, but they cancel out exactly. So there is a cross term, m1 times this quantity, and there is an m2 times this quantity. They cancel out exactly, so that doesn't exist. Okay. And this has a feature, right? I can cancel out one of them here. This is m1 plus m2 dr by dt square plus, if I take m1, so this is m1 plus m2 cancels out, and what we have is m1 m2 over m1 plus m2. Okay. But then there is an observation that m1 m2 over m1 plus m2 is, or maybe I should write the opposite, right? What do you say this? Yeah. So there is this observation that think of parallel resistors, m1 1 over m1 plus 1 over m2 is equal to m1 plus m2 over m1 m2. So let's define this quantity 1 over m1 and 1 over m2 as 1 over mu. This is what is going to play an important role. It is called the reduced mass. Okay. So we'll call this mu, which is 1 over m1 plus m2. That means to say that mu is equal to m1 m2 over m1 plus m2. Right. With me? So all this leads to the relation that the Lagrangian is equal to the kinetic energy has a simple form, m1 plus m2 times the velocity. And this is the velocity of the center of mass, notice, right? Rate of change of position r has to do with the center of mass's position, plus mu times the relative velocity. Small v is relative velocity difference in the positions r1, r2, and the potential energy is g m1 m2 over the magnitude of the relative velocity. Right? This is the magnitude of the relative velocity. So what does the Lagrangian depend on? What are the coordinates it depends on? It depends, does it depend on the center of mass? Does the Lagrangian depend on the center of mass, the position of the center of mass? Like remember earlier it was r1, r2, so now it should be capital R times dr by dt, and there is a small r, and its velocity, relative velocity, correct? But this does, or the question is, does this Lagrangian depend on the position of the center of mass?
No.
Doesn't, right?
So it doesn't exist there, so that's not there. And whenever it does not depend on it, what does that mean?
It's conserved
That must be a conserved quantity,
variable.
or there should be no motion associated with it. So it's an unnecessary quantity. So if I can sit on the center of mass, so I'll choose a frame and sit on the center of mass itself. This will also be gone. So there is no physics associated with it. So if it is, at the most, it will go with the constant speed. There is nothing interesting in there. So I can get rid of that quantity also. Further, it turns out that it does not depend on the complete position, the relative position. It actually depends only on the magnitude of the relative position. And that will have an important role that will be called a central force. Right? A central force will be whenever the physics of a problem depends only on the magnitude of the relative positions, then it's called a central force problem, and we will talk about that. So, so we are pretty much going to drop this term altogether because there is nothing interesting in there. I can choose dr by dt to be 0, and I won't lose any generality. Like at the most, I can go with a constant speed, but I can always go in a frame where that is having a constant speed, and that would be gone. So my Lagrangian would be, the Lagrangian of interest for the Kepler problem would be, as of now, the way I have written it, it is R and V, right? Where it turns out that it does not even depend on R completely, it's the magnitude that comes in. So it is 1/2 times mu times velocity squared, right? And plus G m1 m2 over the magnitude of R. Significantly simpler, but notice this is not mass that is coming in. It is mu, the reduced mass, or 1 over m1 plus 1 over m2. Okay, and that makes
So
it
in your expression of L, I think you're missing a half for first two terms. Is there a half there?
Oh, yes, in the first thing here, right? So there should be a half and a half there. I think I was just directly copying that, right? But I did write it here.
Yeah, that's why I got confused. Okay.
And a half bit catch. And then I go to the rest frame of the, or I go to the center of mass frame, sit in there, and then that's your Lagrangian. Okay. In fact, I can immediately write the Euler-Lagrange equation at this stage, but we will do a little more feature in there because it is still a three-dimensional problem here, right? Three-dimensional in the sense vector R could be in X, Y, Z plane, but we want to first make sure that the problem is in a plane. The Kepler problem, the orbit is always in a plane. So first, let's identify that, and for that we will invoke angular momentum conservation. And once we have that, then we get the ellipse as an orbit. Have you guys calculated ellipse to be an orbit before in any course?
I think so.
Other than accepting it as it comes from Kepler's laws?
I think it was discussed. I think our professor did worked on it on the board, but I'm not sure we actually did it.
Okay.
Yeah, I did that in Kepler's.
Calculus, yes, that's a good place to do that. Yeah. So is circle and orbit, is circle allowed? Like ellipse is okay. Is circular orbit allowed? Can a planet go in a circular orbit?
No.
No.
Yes. Two comments, others. Angela and
I feel like the answer is no, but I don't know the explanation for why it's not. I mean, we don't know any
Like
planets
it's,
going around in circular orbit.
Well,
It's
there is
only-
something, well, we have to take into account of eccentricity
okay.
and if we take circle, everything becomes zero.
I think you can do it mathematically, right? But I don't think I don't think we know of one practically when you
Yeah.
add third bodies, fourth bodies, fifth bodies. But I think you can work it out on a piece of paper in a two-body system, right? To be circular.
I think Duncan's statement is, oh sorry, Jordan's. I keep saying Duncan. I think that's because your name is so fancy. Yeah, okay, Jordan's. I think your comment is much closer. As far as mathematical solution goes, circular orbits are allowed, very much allowed, and
It's just an ellipse,
quite
right? Just
common.
a special case ellipse. The circle.
Yes, exactly. Any what's that called? A parabola, ellipse, hyperbola, and circle, the whole of them together. Conic section.
Conic
Right?
section.
So any conic section is a solution of a couple of problems, and circle is a very particular case, so it's less common, but surely allowed. Depends on the initial energy, and we will see all those cases. It pretty much once you get the orbit, it immediately comes out why. What are the four cases? So it's nice to see those solutions. So we'll do that next time. At this point, I think I should let you guys go. We have Anil's defense at 11:30, correct? On Zoom, so easy to attend actually. So I'll try to attend that. And before that, I should work a little for the next class I have at Angela.
Well, don't we need the link?
There is an email that I got.
I'll forward it to you, Avinash.
I don't think I got it though.
Okay, Moses,
We
can you
didn't send it to the undergrads. Yeah.
Yeah, I'll send it to you.
forward that to Avinash? Yeah.
I got the email about Aaron's master's thesis defense, but not Anil's.
Well, I didn't receive that, so that's interesting. Okay, I'm biased here. Okay, Moses, can you do that? Do me a favor, forwarding
Yeah,
that to.
yeah, no problem. I'll send that to him.
Thanks. Okay, thank you. And yeah, I think I did very little today, but I think discussions are also good.
So I have a question really quick before you go.
Sure. Go ahead.
Why do you know, if circular orbits are possible, you know, why do they get really close to circular but not exactly circular?
We will see that. I mean, once we have the solutions, it will come out clear as to only when the total energy of the system is having a very particular value, you get circular orbits. The same thing with parabolic orbits. Are parabolic orbits allowed? Do you see any planets?
No.
Again, you don't see it, but it's an allowed orbit. Okay? Like right on the boundary of ellipse and hyperbola is the parabola, and that's also
in a two-body system, they're allowed.
System. Yeah, in a two-body system. Yes, we'll see that. Okay? Again, very likely, I'm sure somewhere in some planetary system there is a object that has that orbit, both parabola and circular, but it's just that the chances are low to have that configuration, just because the chances are low, not because anything. It's not because of instability or anything. You can have an initial energy from 0 to, let's say, infinity. What are the chances that it will have exactly 1? That's the question you're asking.
Okay.
Actually, exactly 0, I think. If the energy is exactly 0, it is a parabola, and if it is exactly equal to the potential energy, then it is a circular orbit. So that's what happens.
So can you have like a spherical orbit?
Spherical, no, because it has to be in a plane. We haven't come to that yet, but angular momentum is conserved. So since angular momentum is conserved, it has to be in a plane. No
Okay.
choice. That's why most of these solar systems are flattened, right? Galaxies are all kind of a disk kind of quantity.
So,
Spherical
okay.
galaxy.
Okay.
Hey, thanks, Moses.
Other again?
Thing.
He sent him the email, I think.
Yeah.
Okay.
Good.
For some reason, I keep on picturing a parabola as half a, like if somebody cuts an ellipse into two, then I get parabola. For some reason, I think that.
No, it's not. It's not. It's not.
I know. For some reason, I picture that.
Yeah. You guys know the conic sections, right? You take a
Yes.
cone and
Yes.
right,
Mhm.
do one cone on the other and slice it. That's how you get these all the conic sections. Have you guys heard of that?
Yeah.
Yeah.
Look it up, conic section, geometrical visualization of conic sections.
It's like this intersection of cone and planes.
Yes, exactly. Slicing, I think of it as slicing a cone with a plane. Yeah, that's correct. Yeah, whatever we say. Yeah. So, yeah. So we'll see all those results coming out of our solution. I think tomorrow in the next class I will have the solution, and then we will be able to talk about how all these statements fit in.
So you would say you could have circular, elliptical, parabolic, and hyperbolic.
Symbolic, yes. So
Those are the
four
only
solutions.
4 ways that you could.
You can have a planet go around the sun.
Okay.
And we see only 2 of them. Elliptic, these are the bound orbits, all the planets. And the hyperbolic are the comets, like one-time coming comets. There are comets that come once and they go.
So what's the difference between like a hyperbolic and an elliptical? Because wouldn't they be like pretty the same?
No, let me draw that.
Like they have the same structure, right?
No, one is the bound orbit. So, for example, you have this is the sun, right? This is an elliptic orbit, right? And hyperbolic would be this will go to infinity and come from infinity. Is that clear? Like it comes from infinity and goes to infinity. It will never come back. It's a one-time visitor. Right? A hyperbola doesn't close itself. It's an open orbit.
Okay. The same with the parabolic?
Parabolic is also a open orbit.
Okay.
So there are comets which come only once. And there are comets that come again and again, but with a period of about 100 years or so. They're all ellipses with a very large eccentricity.
Okay. That makes sense.
Yeah.
But their eccentricities or whatever would be similar or not?
No, eccentricity of 0 is circle, eccentricity between 0 and 1 is ellipse, eccentricity of 1 is parabola, and eccentricity of greater than 1 is hyperbola.
That is correct. So eccentricity is a parameter that classifies this, whatever we talked about in the poll.
Okay. Okay.
Again, we will define this for our problem in the next class. So it will become very concrete. And so there will be 2 parameters that decides the orbit. One is angular momentum, that decides how much initial energy there is, and the second is eccentricity, which basically is the velocity. Like initially, how much velocity you have. So that will pretty much set the orbit for life.
So to get a spherical orbit, you would have to give it some sort of like up and down motion?
No, spherical orbit, what do you mean by spherical orbit? It's not allowed. It has to be planar. Remember, angular momentum is conserved. So it has to be in a plane,
Okay.
right? So to begin with, anything on a sphere is possible, but once the motion begins, it's in a plane.
Okay.
So sort of, it's constrained. That's not the case of a pendulum moving in uniform gravity, I think. Right? Is angular momentum conserved there? Probably not. That's slightly the same. Spherical pendulum is slightly different from the Kepler problem. In Kepler problem, angular momentum is conserved. At the moment angular momentum is conserved, there is a vector which is constant, and the motion happens in the plane perpendicular to that direction. Again, we will see that, like, we are going to invoke that symmetry next class in the very first few minutes, so that first we will convince ourselves that motion is in a plane. Then there are only two variables, and that will simplify the calculation of derivation significantly.
Okay. All right.
Okay, good. Nice discussions. Yeah. Thank you, and thanks for
Thank you.
staying longer.
Thank you.
Okay. Good.
Thank you.
Moses, I'll see you later, I suppose.
Oh yeah, at 2 o'clock. Sounds good.